Of content for this.
So we're gonna bust through it. Watch your video later.
All right, let's go through logistic.
Okay.
Since that's gonna be the meat and potatoes. What? I just realized I didn't print out his logistic
Does anyone have an
concept list.
I have it on my computer. We can open it.
That's okay. I can pull it up on my phone.
All right, you guys have the list right in front of you, the concept list for logistic. So tell us if we missed something. Okay. Oh, it's in our email? I'll find it while you talk.
All right. So, walled statistic and its limitations. So in SPSS, it's found in the variables in equation table. One of the things you need to know about the walled statistic is it's affected by large B weights. So if inflated or large, the walled statistic might not be correct or accurate. So, huh? Yeah.
At first, are we logistic concept list? Are we going in a row?
Probably not.
Okay.
Probably not. So for large coefficients or large B weights, standard error is inflated, so it increases the likelihood of making a type 2 error. Yeah, so for large coefficients or large B weights, standard error is inflated, thus it increases the type 2 error rate. Walled statistic is like a t-test in multiple regression. So it's a relative measure used to test the statistical significance of each coefficient. I'll say that again. It's a relative measure used to test the statistical significance of each coefficient. And you look at each coefficient, or you look at each B weight, which is a unique contribution of coefficient in the model. Yeah, so the walled statistic is looking at each B weight as its unique contribution in that model. Mm-hmm. Do you want me to do the limitations? Sure. Is that all you want? No, I have more stuff on here.
Is there any way that you could repeat what you first said? I was opening up an email.
About SPSS and the variable.
For large efficients or for large B weight, standard error is inflated, thus it increases the type 2 error rate.
Yeah, so it's affected by large B weights. So if it's inflated or large, the walled statistic might not be very accurate.
So you guys should label that as a limitation.
Yeah.
In your notes.
Where was it found in SPSS?
It's in the variables in equation table. So another way to think of the walled statistic is it's used to evaluate B weights greater than 0. When it's close to 0, it suggests that there is probably no change as a result of that coefficient. So I'll say that again. So it's used to evaluate B weights greater than 0. Close to 0 suggests there is probably no change as a result of that coefficient.
It's pretty. Well, girls in a casino or something.
Do you wanna?
I think that was that's pretty much it. That was it for the limitation. So if you have a large B weight, you may go down to everything chi-square, even though
What was the top end?
it is. Did we say that?
Huh?
The top end for that statistic was at 1, like highest theoretical value required. Get a range between 0 and 1.
I believe so. Do you have that range for it?
I'd like to see expression, because it means I'm the only one that's like,
I don't have that either, so. Oh, close to 0 probably suggests there's no change.
Yeah.
Do you guys know what makes logistic regression? Like what types of stuff you need for it? What variables? So the DV has to be categorical. Okay, and what about the outcomes? Categorical, and the outcomes are dichotomous. Nope, this is just logistic in general. This is what, like when you would use. So again, the DV is categorical, and then your outcomes are dichotomous. Okay. Yep. And so if you are ever confused about like when you use what statistic, really just refer back while you're studying to your decision tree. And now that you know more about each of these types of stats, it should be easier to follow the decision trees. I think some of you probably are feeling like those quizzes are a little bit easier, just because you may know a bit more about hopefully you know more. All right, so next I have the log likelihood ratio test. Yeah. Let's see what he calls it. -2 log likelihood. Yeah. I think that's the same, right?
Yeah.
Okay, so it evaluates to see if the set of IVs improves the prediction of the DV better than chance.
This is -2 log.
So again, it evaluates to see if the set of IVs, or in this case, I think he calls them IVs, right? Yeah, if the set of IVs improves the prediction of the DV better than chance. Okay, so it assesses if at least one of the IVs is statistically significant over 0. It assesses if at least one of the IVs is statistically significant over 0. Okay, so this is a type of a fit statistic. Okay, and you might want to use this over the walled statistic if you have smaller samples.
Over the what statistic?
The walled, it could be more reliable for smaller samples.
Wait, you'd rather use this one or the wall?
This one.
For smaller samples, rather use this one. The lower the score, the better, because it means better fit of the model.
The lower the score, the better.
Because it's a better fit for the model.
A little lost because this is significant.
It's a fit statistic.
It's statistical.
Yeah. So if you notice that, like from each block, your IVs, like if you notice that the statistic, the value is getting smaller, it means that the IVs are better predictors than the of the DV than compared to chance. So it kind of goes back to the definition again. Okay, so in each block, if you notice that the statistic value is going down, that's a good thing. It means that your model is fitting better than chance would. Does that make sense? Sort of? Okay. And in SPSS, you find it in the table called Model Summary.
Is it true it's also a summary statistic? I have that right now.
Yeah, I mean, maybe because it's in the Model Summary table. Okay? All right.
Pseudo R squared.
Okay. Pseudo R squared. I don't have that one, so. Oh, here it is. Ooh, is this the Nagelkerke?
Uh-huh. So pseudo R squared, it's found in the model summary section in SPS, in your SPSS output.
Is that on your thing?
Is this the one?
Yeah, this is the Nagelkerke.
That's the one.
It's in the parentheses.
Yeah.
Yeah, so this is it.
Yeah.
Like pseudo in quotes.
Yeah.
That's like an R stuff known as everything.
Nagelkerke R squared.
Yeah. So the tests are the Cox, Snell, and Nagelkerke. And those all range from 0 to 1. So this is the best way of estimating the percent of variance accounted for in a logistics test. Yeah, it's the best way of estimating the percent of variance accounted for in logistics tests.
And is this just the percent of variance accounted for by the model?
Yep.
as a whole?
Exactly.
Is this, there's one type squared.
This isn't it. This is already squared for you.
Yeah, because don't square it. So if, I mean, example I have is if it's 0.317, what percent would that be?
31.7.
Yeah, so like 32% of the variance is accounted for by the model.
Yeah, this is the one that's already squared. This one gives you,
Okay. There's further being like one that you have. Like,
there is one,
theory
and
of
it's,
squared. It's in the alphabet you gave us.
All right. Do you have,
it's the conical correlation one. So you want it obviously to go up from in your model.
next are the classification tables, and I think you guys are familiar with this from Dr. Mono's class, hopefully. Okay, so this table lets you see how accurate your predictions actually were.
Canonical correlation.
Nope.
Classification.
tables. We didn't do that one yet. Classification tables show you how accurate your predictions were. So you guys should know, he said, how to read the table. Okay, so don't assume that the table is going to be set up the way you think. Actually go through and read what the headings are. If the example he uses doesn't make sense, make up your own example, something that's more realistic. So what is it used for? What are the two S words?
Specificity and sensitivity.
Yep, specificity and sensitivity. Okay, and for example, one of the sections is the hit rate, right? So what does that represent?
You're making sure the
The true scores overall of them. Yeah, so how many, so when you were right.
So it's the number of true positives and true negatives. Nope, just the number of true positives and true negatives added together.
over.
It turns into a percent of the correct prediction.
Right.
You put that over.
Yes.
So it's like
Yeah.
2 squares over the total of the 4 squares.
Right.
Or backwards model is like A plus D.
Yeah, that's what I have in my notes, because I
Yeah.
was taking her class too.
Translated to what we're going to be doing.
Yeah. So you can get false
No,
positives.
yeah, it's the sum of the true positives, true negatives over the sum of everything in the model.
Because think about it, like think hit is like a good thing. Like you hit it on the head, you got it right. So you correctly predicted that these people would be positive, and you correctly predicted these people would be negative. So you get false positives, false negatives, and true positives and true negatives. So let's do, I guess it makes sense, what's specificity? To do that one next. So which of those 4 is specificity? The true negative. Okay, so you're finding the people without the problem.
That's where the false negative, false true negative.
Okay, so this is the ability to pick up people without the problem. So this would be like,
No, it's just true negatives.
these would be your true negatives over your false negatives plus your true negatives. It's your true negatives divided by the sum of your false negatives plus your true negatives. So in Dr. Mono's thing, it's D over C plus D is how I have it labeled, if we drew it the same way.
I would just rotate the numbers like let's see it.
Okay, and then what about sensitivity?
Yeah.
True.
I got like 8
I've modeled stuff.
over all of those ones.
Yeah, the sensitivity is the true positives over everything that is positive. So true positive divided by the sum of true positives plus false positives. Okay, so this is important too. This is how good you are at finding people with the problem. I think she gives the example of like, or even Gevirtz did, of like a medicine or you know, for a disease or something. It is really important to be able to find that small amount. Okay, and sometimes sensitivity is more important than specificity for that very reason.
So how will you find the people that have it?
Yeah. Which you want to be good at. Because if you miss it, then, you know, somebody could be walking around with cancer, right? And they don't know.
So what SPSS gives you for the hit rate, you know, those two, that's the percentage.
The hit rate, yeah, is the true positives plus the true negatives. So that's different from sensitivity and specificity. Okay. All right, what else?
Base rate was covered. That's it.
I don't know.
Yeah.
Base rate. All right, I have next. Do you have Cohen's Kappa?
Yeah.
It's not on here though.
No, it's not.
Do you talk about Cohen's Kappa?
You went so quickly through everything.
You did a, what did you say?
Cohen's Kappa? All right, let's do the, what is it? Hosmer, Holmser, and Lemschau? How do you pronounce it? Hosmer? Okay, this is just the difference between the observed and the expected value. And for this, you do not want significance.
Value of what?
I think it has to do with, let me see about this one. This was, I think in this SPSS, it's with the contingency table, the chi-squared. Do we have? Yeah, is that right? It's in the slides? Oh, it's in the review guide, okay.
Oscar, is it literally called that? 5 instances?
I think so. I don't have that. I don't have the output.
Oh,
Okay. All right, what's next? Do you want to do the assumptions?
Mm-hmm.
Okay.
Okay, so what are the assumptions of logistic? There's the absence of perfect multicollinearity. Now, what is multicollinearity again?
Things are too correlated.
Yeah.
Right.
Okay.
They are not, so they're more independent.
Mm-hmm.
Mm-hmm.
Factors.
Yeah, IVs are independent. There's no autocorrelation, which is independence of observations. And it's assessed using, again, the Durbin-Watson. You're looking for 1.3 to 2.7.
There is no autocorrelation.
Right. You want independence of observations on that one.
What was the numbers you were saying for the?
1.3 to 2.7 for Durbin-Watson.
That's what you want.
Yeah, you want something in that range. 2 is that normative value. It's a non-parametric test.
The autocorrelation.
No, the assumptions of logistics. It's a non-parametric test. Right, what do you have there?
Oh, on my list?
Mhm.
Yeah, non-parametric test, normal assumptions of regression equations don't apply.
Yeah,
Specification, did you say that?
no, not yet.
That wasn't, okay.
So, and the last one is specification. How well predicted values match actual. You want to make sure there are no systematic errors.
Is that the Hosmer-Lemschow?
No, these are the assumptions for logistic.
I know, but we test specification of that. You said that the Hosmer-Lemschow is the difference between expected and observed.
What test did we always use for specification? Is there a particular?
Does somebody have an example logistic output?
Yes.
Here. Oh, I think I have this for you.
Okay, thank you.
Yeah, so with the Hosmer and Lemschow test, like we said before, you want a good fit between what's expected and observed, so that's that contingency table. But let's see, specificity, let's see if it says.
I thought I remember him looking at the chi-squared for evaluating specificity.
And
This
here.
chi-squared is the
Yeah,
Hosmer-Lemschow.
but in the omnibus test of model coefficients, under block 1, it's the first block that you look at. You evaluate that table as far as model fit. Let me double check with him. And I'll email him and then we'll get back to you just to make sure.
I have this one.
Because the
Yeah, I
one
was
you
gonna-
want certificate, the other one you don't.
Right.
And the Hosmer and Lemschau test has to do with homoscedasticity. I don't know if you guys wrote that, he said it during class.
Yeah.
So, but let's get back to you about the other question. Okay, what's next on the list?
Put it down. Does he have contrast to discriminant analysis on that one?
No, but you guys know the difference between logistic and discriminant analysis? Logistic regression and discriminant analysis? Okay, so we know logistic regression uses what types of outcomes? Dichotomous, okay. In discriminant analysis, this is when your predictors must be continuous.
So logistic uses.
Outcomes. Dichotomous outcomes, and discriminant uses continuous predictors. Okay, for logistic regression, you need more subjects. And it's less restrictive.
So some other things that are unique about logistic, it doesn't have to be linear. There's no homogeneity of variance assumption. It doesn't have to be homoscedastic. The DV doesn't have to be normally distributed. And it's a non-parametric test. It's also less restrictive than discriminant analysis.
All right, let's do.
Less restricted also a factor of discriminant analysis.
It's less restrictive than discriminant analysis. Logistic is.
Logistic is less restricted than discriminant. Was discriminant less restricted than anything else? I might be confusing. Because I thought the discriminant analysis was the one that we were just discussing, that had predictors must be continuous, need more subjects, less restrictive, and the economist outcome.
You may, no, you.
This is all in the heading of.
No, you switched some of those things. So, discriminant analysis, the predictors must be continuous. Okay. Logistic regression is less restrictive. And logistic regression needs more subjects.
Yeah. So for logistic, the predictor variables can be continuous, dichotomous, or categorical.
For discriminant.
For logistic regression, predictor variables can be continuous, dichotomous, or categorical. In discriminant analysis, predictors can only be continuous.
Good? Okay. Is that what you said out loud?
No, not
Okay.
at all. I was way off in the grass.
Okay. All right, so let's do the odds ratio. Gevirtz talked about this on page 3 of the output of the logistic regression packet, if you want to follow along. So when you're looking at SPSS, is that?
Yes.
What does that say?
I think it was exponent.
Okay,
but-
so it's in the table called variables in the equation. Okay, and it's the one that's labeled EXP with the B in the parentheses. Okay, so that's where you look for odds ratio.
You will repeat that, sorry.
Hmm?
Not an SPSS,
It's in the table called variables in the equation. Okay, and it's the heading of EXP, parentheses B, big B. Okay, so for this, you're only interpreting what's significant. And you can see the significance in the column right next to it.
Are we just specifically talking about the odds ratio?
Mm-hmm.
And I'm sorry,
You only interpret the odds ratio or the XB when it's significant, and the significance is listed right next to it.
so you want to significant?
Mm-hmm. Okay. If you take 1 minus the value that you're given in the column EXP with the B, okay, that gives you a percent. Okay, if your odds ratio value is less than 1, it indicates an inverse relation. Okay, so how does the review guide? Sorry. Probability versus odds ratio. Okay, so odds are the probability of belonging to one of the dichotomous outcomes. Probability of belonging to one of the dichotomous outcomes. My notes are really messy for that.
So the way to read it,
I didn't say that either, I forgot. So it's between 0 and infinity. We should go back up to this end. Let's skip some of this.
yeah. And it's the probability of belonging to one dichotomous outcome. So the way you read it is a 1 unit increase in predictor increases the probability of the outcome by whatever the value of the odds ratio is.
1 unit increase in the predictor increases.
The probability of an outcome by, and then whatever the value of the odds ratio is, when holding everything else constant.
What was the 1 minus the XB then? Isn't it, that's what, if it's significant, that's what number it increases by?
That's the percentage.
It's the percentage.
So, it'd be like.
Because it's a ratio, so you can do, you can divide it. But in this case, they just subtract it from 1.
But like our number is like 2.2.
So a 1 unit increase.
No, but the 1 minus.
Okay, I see what you're saying. Do you have that in your notes? The 1 minus?
No, I just have that it was 1 minus to get the percentage of,
Yeah.
I believe
The
it
way we
was
write it in class, it's just, 1 unit increase in your shared cookies increases the likelihood of finishing on time 2.21 to 1.
Okay.
Which is more constant.
And I think that's the more important. So if you guys want to forget what I said about the 1 minus, that's fine. If that's more confusing, I don't think that'll be on there. But what Amber said with the,
Is it wrong or?
I don't know. I mean, I have it in my notes, but I'm not sure if it's wrong. Okay. Yeah, I'm not sure about the negative, because when you subtract it. I don't know if you just get rid of the negative and multiply by 100, I don't know. So, I'm not sure, so I don't want to tell you the wrong thing. But I wouldn't worry about that.
It's the odds ratio, 1 minus the log.
It's 1 minus EXPB.
Which is the odds ratio.
It's nothing to do with the log, right?
I don't know if in this part. But don't worry about that. Know about the 1 unit increase. Okay, that's the most important part. Okay? Everybody good with that?
And then I think I have.
They had to allow the B weight. With your probability.
And then probability is the last one, which is the likelihood of event occurring. And it ranges from 0 to 1.
But we have to be able to convert the negatives, though, right?
Yes.
Okay. So you guys go with probability in the table, the percentages and stuff? Okay, what's next?
Can you explain binary
Binary, yeah. Because, again, it's classifications of zeros and ones. It's how you code the data.
Yeah, that's done.
Right. That's, yeah.
Yeah, so you just give numbers. Excuse me. Okay, what's next? He doesn't have the adjusted odds ratio.
You dummy code things based on somebody falls into a category. So 1 indicates yes, they fell into a category, 2 indicates no. Or 0 indicates no, not 2, sorry.
So you guys remember in the output he went over, he said that B weights are like logs? Okay, so I think that's what that means when he listed B weights. And standard errors, that's like the Monte Carlo study.
Does he have influence statistics on his output? I guess from another exam.
Okay, the 2 log likelihood, that's on there, right? That's, or the negative 2 log likelihood? Do we do that one? Okay. What are we missing? Standard error. That's like the Monte Carlo. Okay, that's the standard error of the B weight. When it's talking about standard error in that table, it's the standard error of the B weight. Okay. What else are we missing, guys?
If it's inflated, or just with the standard error, if it's inflated, that's what affects the walled statistic.
Because you're the B weight over the standard error, you get the result.
Yeah, so it causes distortions. That's why the walled statistic can get inaccurate, is due to the standard error. So. Yeah, that's a really good question. I'd ask Gevirtz.
So it's not like it's really good.
Right, like Yeah, and it's not like there's a cutoff where if it's like above a certain number, it's inflated. It's, you know, it's gonna vary from test to test.
So for some reason in our notes, we both have influence statistics.
Mm-hmm.
Okay, and those were from the first exam, but they're not on your study guide, but I may just glance over them real quick. So those are the Cooks, the leverage, DF beta, Mahalanobis. Okay, so just remind yourself of those. I know. Cooks, leverage, DF beta, Mahalanobis.
Yeah.
What about the Cohen's kappa that you said earlier?
So it looks at inter-rater reliability. And it's an agreement statistic that corrects for chance agreement. And the way that you do that is you take the hit rate over the non-hit rate for chance agreement.
Is that for the influence statistic?
This is for Cohen's kappa. This is how you determine inter-rater reliability.
You said it looks at inter-rater reliability and
That's it. It just looks at inter-rater reliability.
That's all.
So it's not an influence statistic.
Correct.
Before we move on to something else, when they were talking about before converting a negative B log, if you have one that is one of the predictors that's significant but it's negative, is that when you do the anti-log?
Mm-hmm.
And then what do you use that number for again? It's the odd ratio.
And then that's where you can say about the increase or the but then you would you say decrease? Yeah.
And I think he went over that one in your handout that he gave you. I thought I saw anti-log in here. Yeah, so on page 3 of the logistic regression output, slide 4, he talks about the antilog.
What about the equation?
You know the negative weights?
Mm-hmm. Yeah.
Is this the equation?
Goes over as you want to know, what is it?
It's just the equation.
Oh, the logistic regression equation.
we did the not-log, anti-log, and match the negative.
Yeah. So basically review your slides for all of the log equations that he goes through. He's not going to actually have you do them and calculate them, but you should be able to recognize them.
What's the maximum likelihood? I don't know what the maximum likelihood estimation is. I've never heard of it.
It's something different than what we experienced. It's on the mark one. It's like the predictor over like 1 minus the predictor equals the predicted probability.
Is that the MLE?
Yeah, that's the MLE.
The MLE? Okay. Okay. Bueno.
What's the safe scores?
Where is that? Do you know what that is?
The what?
Saved scores? I don't know. We can ask him now.
Yeah. Did he go over something like that in class? All right. I'll email him about that one.
Okay, what's next? ANCOVA?
Did you need the classification table?
Yep,
Yeah, we did.
that's with the hit rate.
Scores like factor scores?
I'm not sure. We'll ask them. So maybe factor scores. Okay, where's the ANCOVA?
Concept list. It's on that long one I gave you.
This is brutal. Brutal! So we're not doing meta-analysis?
No.
But we're doing ROC curve. Okay, let's do that really quick. ROC curve concepts. So sensitivity versus false positives. This is where you want to maximize the area under the curve. Okay, you want the best balance between sensitivity and as few false positives as possible. Bless you. The last one? Yep, and you want the best balance between sensitivity and as few false positives as possible.
So the amount of area under the curve shows the success of the model to predict or classify correctly. Yeah.
No, that's, oh yeah, you were saying the next one. The whole thing, no, ask somebody else, sorry. We don't have time. Okay, area under the curve. That was what Amber just said?
Yeah, so the amount of area under the curve shows the success of the model to predict or classify correctly.
Because think about it, if it's under the curve, it's contained, it's included, yay, it did a good job. Okay, we good with that one? Okay, and then the cutoffs. You need to decide the cutoff values to maximize the area under the curve. Okay, and it just depends on where you draw your line.
Right. So just know that the closer it is to that 45-degree angle in the center of the graph, that's the cutoff at chance. And the closer it is to that 45-degree angle, the worse the model is.
It's better up here, right?
Yeah.
Does he want it to be better than chance?
Right. You take anything above that line, that line in the center of the curve, that's drawn in the center, that's your chance cutoff. So anything above that is better, but again, the closer you get to that line, the worse off your model is.
That's better with the star.
Right.
Okay. So just remember up and to the left. It's better. Okay. Yay, look, we did a second one.
Okay, ANCOVA, and I think this is the last one, right? We've kind of gone through the discriminant concept list when going through.
Is ANCOVA confusing? Okay.
Okay. So what are covariates then? That's the big thing in ANCOVA. Huh? Right. Well, it's the variable the researcher is controlling for. So in an ANCOVA, we believe that there's this variable that's contributing to the variance in the model. And so we want to partition that variance out of the IV and the DV relationship. So when evaluating whether or not to use a covariate, you want to look to see if it's significant. Because when it's introduced into a model, you automatically lose 1 degree of freedom. which means you've lost 1 degree of power. So it's a decrease in power.
When it's introduced into the model.
Mm-hmm.
It takes up a degree of freedom, which decreases your power. Okay, so you really only want to use it if it's going to work, right? You don't want to just waste it. Okay, what's next? Okay, so ANCOVA versus repeated measures.
ANOVA.
ANOVA. Okay, so ANCOVA reduces within group variance. And it, within group variance, and it deals with sphericity. So that's the benefit of using ANCOVA.
Right.
Reduces what again?
Sphericity
Before that?
reduces within group variance. So make sure you guys know the power equation that's going to come up possibly on the test. It'll help you just with conceptualizing stuff. Do you guys remember what power is? Some sample size times effect size divided by within group variance. Okay, so if you can remember that, you may be able to work through some of these problems.
Sounds like this test is going to be pretty hard.
It's going to be a lot of stuff.
It might be
But if you
longer.
think about it, he's testing you on so much stuff, so he's probably not going to get... yeah, I feel like the confirmatory factor analysis test, exam 3, was the hardest one that he did
It
last
was
year.
more detailed, I think. Yeah.
For everybody, I don't, yeah.
Last one?
Yeah.
This last one, the last one.
The past one?
Yeah.
So the non-experimental situations. Let's see, what did I write?
So it can be used when comparing 2 pre-existing groups where randomization cannot be used.
Yeah, groups are pre-existing.
So you find a way to kind of artificially equate groups.
Sometimes the way researchers like break up their subjects or groups helps to deal with some of this variance, but when you can't do that, that's why you're doing this ANCOVA.
Right. Does that make sense? So when you're comparing, let me try and give an example. When you're comparing,
If you're seeing two like ethnicities or something, or are similar enough or different, is that could be what you use? Like if you're seeing very like empirical.
well, this is more like, okay, so you are taking 2 groups that are already in existence, and there is a difference between those groups that's already there. So you remove that out, that's your covariate. So you're finding a way, so because you're removing the variance, because those groups are already created, you're removing kind of one,
Is it right that you kind of talked about the 2 different populations of obese people versus like anorexic people?
right. And so what's the one variance maybe that's there? Like you can co-vary something that's already contributing to those 2 things.
Like weight eating variable?
Right, which would be an odd one to, yes. I'm trying to think of an example for this one that would make sense.
This talks about like libido and the Viagra.
No, in the Viagra.
Yeah, the libido and the Viagra. I think that's from the new textbook. Okay.
So basically, you're trying to find a way to equate the groups already by removing the one difference you know already exists between the groups, and you're partitioning that out. That's your covariate.
And it was something that you couldn't control for with your
Right.
setup.
Right.
Okay, and a note about that is you don't want to use it for quasi or static experiments. So you know how there are like quasi experiments? You don't want to use ANCOVA for quasi experiments.
What's the static experiment?
I never heard of it. Okay.
Reduction of within group variance versus the degree of freedom law. So obviously when you covary something, you lose a degree of freedom. So the degree of freedom loss when you use an ANCOVA reduces the power.
Yes, it does.
Yeah. And when covariate scores are available, we have information about differences between the treatment groups that existed before the experiment was performed.
Because remember, this is a difference inherent in the subjects, and you're trying to remove it. So that's why it's before the experiment happened. Does that make sense? Kind of.
Okay, so here's an example for covariates when it might be helpful. Take forever to think of one. So let's say you have a treatment study that you're running on depressed individuals that are in an inpatient treatment facility, and everyone's on an antidepressant. And you want to compare the effects of two different treatment types. Let's say you couldn't randomly assign these people to the treatment groups, they were already in it. Well, what's one thing that they all kind of can vary their scores? So if you were to move out the type of antidepressant on each and covary antidepressant medication and factor that out, then you could begin to look at treatment alone, right? Because treatment and medication use are going to affect depression outcomes, so you remove one of the variants so you can get a clearer look at treatment affecting depression scores, right? So you're removing medication. So that's what a covariate is doing. You're saying we have these pre-existing groups, they vary along this one domain, but we don't want that to affect what we're looking at, which is the relationship between the IV and the DV, so you remove that piece out. So that's what a covariate, that's what ANCOVA is doing.
Good work.
Seriously slow today.
Okay. Adjusted means. So these are adjusting, or sometimes they're called estimated means. They're adjusting treatment effects after you put in the covariate. They are more accurate if your ANCOVA works. Okay, and they're equal to the estimated marginal means found in the output. Okay, good. And you're holding constant the covariate, which you already knew.
So the assumptions, you've got the regular assumptions of an ANOVA that apply. Normality, homogeneity of variance, independence of observation. Then you add in linearity. You want to look to your scatter plot. If there's a curvilinear relationship, obviously your ANCOVA is going to be of little use. Reliability of measurement. This is more important of the CV and the DV, obviously.
CV and DV.
And homogeneity of regression slope. So what that means is the covariate operates in the same at every level of the IV. So you want to look at the interaction between the IV, you want to look at the relationship between the CV and the DV at each level of the IV. I could say that again. You want to look at the relationship between the CV and the DV at each level of the IV. And so that's the one where you want all of the graphs to look the same. If you violate this assumption, or the consequences are multiple and hard to predict.
Lots of error, type 1 and 2. Okay, and remember you don't want significance between the interaction of the CV and the IV. Yeah. Yeah, you don't want an interaction between the CV and the IV. Should we talk more about linear?
Sure.
Do they
have
know?
any more?
Do they know about that?
Yeah.
In the last assumption, the reliability of measurement, did you say that this is more important in the CV than the IV?
No, it's just important in the CV and the DV on this one.
Back to linearity, which was the first assumption. I have here that homoscedasticity represents equal scatter, which I think you guys know from the past. It lets you know if the model fits. Okay, that's good, right?
Yeah, we said that.
Okay, okay, good. Sorry, just repeating. And then treatment by block.
We didn't go over magnitude of effect, sorry.
Oh.
Magnitude of effect is how much the DV is explained by the IV after partitioning out the effects of the CV. I can say that again. So how much the DV is explained by the IV after partitioning out the effects of the CV. And you look at your eta squared statistic for this one. Or you can look at your D statistic, right? All of your effect size statistics, you can look for this.
And that was from the first semester,
Right.
I think. The very first lecture, I think.
And then the last one on this one is treatment by blocks. So treatment by blocks is another way to increase power. Yeah, it can also control for within group variance by nesting or adding additional IVs.
One more time.
Yeah, so can also control within group variance by nesting or adding additional IVs.
Do you guys know, so besides treatment by blocks, there are two other ways we learn to increase power. So one other way is the ANCOVA, because we said it takes out that within group variance. And another way is repeated measures ANOVA. I feel like this is one of those things where they looked at the test. Should we say that? Okay, and then just another note. The only thing that your preliminary ANOVA can be used for is to see if homogeneity of regression slopes is violated. Okay, so again, the only thing the preliminary ANOVA can be used for is to see if homogeneity of regression slopes is violated. Okay, so you look to the interaction and you do not want one.
I think that's it.
Do they need to know alternatives?
They went over the alternatives too. reducing the finger variance, nesting, treatment by blocks, and additional IVs, yeah.
All right. Next. 9 minutes.
So we went over classification and hit rates, your Wilks lambda, right?
All right, so do you guys know the purpose of discriminant analysis? Okay, it's used to predict group membership.
Conical correlation.
Yeah, but what it is? Okay, so let's start with it.
I don't get the purpose of any of this.
You just gotta memorize it. No, try and understand it. And then memorize it. And then next year, or in 3 years when you go to do your dissertation, you'll be like, oh, I get it. Okay, discriminant functions. So discriminant functions are how you create the equation. So some of these functions include the structure matrix, and structure matrix test for significance. They cannot be compared, and they're like the loadings for factor analysis.
What did you say right before cannot be compared?
They test for significance. Okay, so that was structure matrix. And then we've got standardized betas, which can be compared because they're standardized, right? You can compare stuff that's standardized.
Are we under discriminant functions?
Yep.
Structure matrix and then
Structure matrix, standardized betas. Then we can do canonical discriminant function coefficients can fit here too. And then I have written group centroids. And those are just the means of the groups.
Those are all under structure?
Nope, that's all under discriminant functions. So discriminant functions is your main heading, then you've got structure matrix, standardized betas, canonical discriminant function coefficients, and group centroids. Okay?
Are these like types?
Yeah. Yep. So,
Paper for this test?
huh? So canonical correlation, okay, that's the next bullet, or the next term.
I'm sorry, people have to spend a moment to go back. I didn't organize it properly the first time.
Okay, so discriminant functions, and then there's 4 examples. Structure matrix.
Okay.
Second example, standardized betas. Third example, canonical discriminant function coefficients. Fourth example, group centroids. No. There were 4. Good?
And the group centroids are the means of the groups?
Yep. Yep. So, canonical correlation. This is the percent of variance that discriminant function accounts for. This is the one that you need to square for the percent. Okay, once you square it, it's like that r squared. Percent variance that discriminant function accounts for. Okay. Just don't forget to square it for the percentage. He likes to ask those kind of questions. Okay, and one more thing for this is that it's a multiple correlation between the predictors and the discriminant function. Between the predictors and the discriminant function. Okay, so next, canonical discriminant function coefficients. So if they're raw, they're unstandardized. Okay, these give you the weight for each function. It helps you create your equation. They're just like the raw regression weights. And when you're looking for these in SPSS, they're actually called canonical discriminant function coefficients. Okay? Which was like the title of this subsection of this term. Okay, and then standardized. Again, because they're standardized, it allows you to compare variables measured on different scales. They're like beta weights. And with these, it's hard to test for significance. We do this, right?
When we discussed the canonical correlations, those are not included as a type of discriminant function?
It was the canonical discriminant function coefficient that was a type of discriminant function.
Right, so then the
canonical, just its own term. Yeah, because it's like an R. It's either like an R squared or a Pearson R.
It's a Pearson R until you square it, which then is the variance.
How do you know which ones are standardized and which ones are raw?
The raw are the ones labeled
Structure.
canonical. These are the raw.
Yeah.
Canonical different function coefficients are the raw, and then the standardized say standardized. Okay?
Canonical discriminant function coefficients, those are the raw.
Yeah.
And then above, standardized ones. Okay.
Yep. So if it doesn't say standardized, then it's raw. Do we do structure coefficients yet? Before? Okay. This is the correlation of each predictor variable with a discriminant function. Yep, structure coefficients. It's the correlation of each predictor variable with a discriminant function. Okay, these can be tested for significance. They cannot be compared. And they're similar to the loadings in factor analysis. Okay. Wilks lambda. Okay, so this tests the significance of the function. It's the measure of how well each function separates cases into groups. This one sounds important, doesn't it? Okay, here's a long one. Ready? It's Wilkes lambda still. It's equal to the proportion of the total variance in the discriminant scores not explained by differences among groups. So it's the percent of variance not explained by the model. That's good, right?
Is it true that you can only use the canonical correlation if your Wilkes lambda is significant?
Is that what he said in class? Or were you reading that?
Somewhat connected.
Where are you reading that?
Output equals second page on the bottom summary of canonical discriminant functions.
1 squared, percent of variance that discriminant function accounts for, like an R squared. I think he's just pointing to the significance. He wants you to see that it is significant.
We want it to be significant or not?
The Wilkes lambda?
Yeah.
Yeah. Yeah, because it tests the significance of the function. All right, and then discriminant score. So everybody's good with classification tables, assumptions. It says C MANOVA. You guys go with that or no? Okay, we'll go back to that in a second. Discriminant score. The predicted outcome. It's comparing against the actual outcome. It's generated for each subject. And it tells you which group you think they'll fall in. Okay, and sometimes this is called the predicted value. So here are the assumptions.
So for the assumptions, he does a pretty good review of the assumptions in the slides that he gave you in class this last Wednesday. Just wanted to point out a couple of things. So homogeneity of variance, covariance matrices. In a discriminant analysis, it's really sensitive.
And you do not want significance.
Yeah, you used, to test this one, this assumption, you look at boxes M, which is easily violated.
What is this for?
Yeah.
These are the assumptions of discriminant analysis, and this is particularly the homogeneity of variance covariance matrices. So to evaluate that assumption, you look at boxes M, which is easily violated. And that's the one where he had the 2 boxes. One was the likelihood that the effect exists, the one where it's due to chance, right? He had the 0 and the 1, the predicted. And you want the correlations between the 2 to be similar.
Normality and multicollinearity.
Yeah. So one last thing about boxes M, it's robust against normality, but not homogeneity of variance covariance. So if you have it, if it's violated, you want to check other things like skewness or look for outliers. Huh?
If everything else is okay, you can ignore it.
Well, when you're talking about normality, but with homogeneity of variance, covariance, again, you want to check all of your other assumptions. So your F max, you want to look at that. Box M is another way that this is going to show up though. But if it's violated, it could be due to having the presence of an outlier, having skewness, which if you correct, then it may correct boxes M. So you can do these other things to figure out if you can get boxes M to be corrected. Yeah.
Yeah, read through this packet. Some of the assumptions are old, like linearity, independence of observation, some of the stuff you know. Normality, the
discriminant analysis handout that we gave you on Wednesday with the slides. And so the last thing is, he said that there's going to be a lot of logistic stuff on here on this exam, so pay attention to logistic. And you'll also want to be able to know the differences between some of the tests. So remember how we talked about the differences between logistic and discriminant? You'll want to know those.
Between the different types.
And what
Like
they do.
What they do, why you would choose one over the other. Same thing with ANCOVA and the other options. So like treatment by blocks, you know, that kind of thing. Okay.
So for that, would you recommend a decision tree?
Yeah, you could review your decision tree, but we went over all of the differences. When we went over logistic, we hit on some.
I recommend flashcards
All right.
for some of the, like, what you need kind of things.
And then I'll ask him about scores saved, and then what was the other one we were going to ask him about? Right, with the EXPB. He actually talks about it in the logistic slides.
I know, it was like the 1 minus the odds ratio.
Oh, 1 minus odds ratio, thank you.
Again, be familiar with the classification table. Those could be really easy questions to get right, since you're already learning in another class. Okay. Bye. Sure.